Hello, everyone. So today we're going to be taking our topics of thermodynamics and actually applying it to chemistry. Welcome to Actually Thermochem. So this is an important idea, as you can imagine, because we're chemists and we like for reactions to happen. And so far, all we've been really doing is looking at changing conditions, so changing volume, pressure, and temperature, and that's more or less been it. But one of the things that we're going to be most concerned about is how energy changes during the course of a chemical reaction. Is the reaction going to release heat? Is it going to absorb heat? These are important considerations. And typically, we're going to be focusing a lot more on enthalpy and kind of ignoring internal energy. And one of the biggest reasons why is because enthalpy is going to be much more a measure of heat, of energy change, or the heat being released under isobaric conditions, which is typically where a lot of our measurements are made under relatively constant atmospheric conditions. Internal energy under isochoric conditions is more exclusively used in a lot of chemical engineering and indeed in a lot of physics, where you're looking at more solid state systems and fixed volumes. And so one of the biggest things we're going to need to start with is simply try and figure out what our standard conditions are. Because as we've pretty much spent the last couple lectures talking about, turns out our internal energy changes a lot based on volume, pressure, and temperature. So if I'm looking at enthalpy, it means I need to have a constant reference pressure and temperature because my enthalpy will change if I change either of these parameters. And again, also the number of moles, meaning we often focus a little bit more on molar enthalpy than just standard absolute enthalpies. And so typically what we're going to be doing is we're going to be focusing in under standard conditions under 1 bar and room temp, or 25 degrees, 298. And we're going to be trying to evaluate change in enthalpies for reactions under these standard conditions. And it turns out that because enthalpy is a state function, we can determine our enthalpy change for reaction simply by knowing the enthalpy of our products and our reactants. So let's go ahead and try and focus in on one of the simplest reactions, which is going to be a phase change. So while not a true chemical reaction, it shares a lot of the same thermodynamic properties as we're making and breaking bonds. In this case, they tend to be intermolecular forces. So what we can do is for a phase change, if I'm going from liquid to gas or a vaporization, I can simply take the enthalpy of the gas minus the enthalpy of the liquid. And for fusion or melting, I'm going to take the product liquid minus the solid. And that's more or less all it takes to try and determine simple enthalpy changes. However, one of the most useful features of enthalpy being a state function is that I can use well-known reactions, say I may have calculated values for vaporization and fusion, and combine them together to describe whole new reactions, like say sublimation, where I go from a solid to a gas. And that's going to be the same thing as going from a solid to a liquid and then a liquid to a gas. So I can essentially, for sublimation, which is gas minus solid, that's going to be the same thing as vaporization plus fusion. And so this forms one of the most important features of thermochemistry, which is called Hess's law, which is more or less just a fancy way of expressing the property of enthalpy being a state function. That as long as I can essentially combine together chemical reactions, I can combine or add together their enthalpies to get my new net enthalpy. And this is going to be a really powerful function, as with a small subset of reference enthalpies, I can quickly describe a whole world worth of chemistry. And we can also apply these same basic ideas for a lot of our relationships between our phase changes, because if vaporization is gas minus liquid, condensation is going to be liquid minus gas. So the enthalpy of condensation is simply going to be the negative of the enthalpy of vaporization. And we can do the same thing with fusion and freezing, where the enthalpy for the reverse reaction of any forward reaction is simply going to be its negative. Now, one of the useful things we can do is, again, try and determine any reaction as long as I have the enthalpy of the individual species, and then take products minus reactants, and again, making sure to scale up for the number of, for the stoichiometric coefficients of each one. Because again, we can imagine for the, when we're talking about the enthalpies of each individual species, we tend to talk about the molar enthalpies for each species. So I need to know how many moles there are per mole of reaction. And that's really what our stoichiometric coefficients really essentially deal with. However, we end up running into one of our old friend problems, which is the fact of how do I describe the enthalpy of a given species? Well, it's the same problem we ran into with internal energy. There's just way too many types of energy inside an individual molecule. And so what we often need to do is express some sort of reference condition for any given species. And typically when we're talking about reference enthalpies, there's two classic choices. And that's going to be, they're both going to be based on the enthalpy of a given set of reactions. So the one you're probably most familiar with from general chemistry is the enthalpy of formation. So this is going to be the amount of energy needed to generate 1 mole of product from its elements in their most stable state. So let's say I'm making sugar. So good old glucose. So it can be made from carbon, hydrogen, and oxygen. And so the most stable state of carbon is going to be graphite. The most stable state of hydrogen is going to be H2 in the gas phase. And the most stable state of oxygen is going to be O2 in the gas phase. And so this reaction is going to give me my enthalpy of formation. So whenever we're talking about the enthalpy of glucose, we're typically going to be referencing this enthalpy of reaction simply because I don't know, there's no other good way to encapsulate how much energy is in that species. Now, as long as all of my enthalpies are enthalpies of formation, essentially what I've done is I made a thermodynamic cycle that's constantly referencing back to the elements. And so it's a fairly consistent method. However, watch out when you're combining it with other reference enthalpies. The other most common, typically used in a lot of engineering, is enthalpy of combustion. So the enthalpy of combustion is going to be the enthalpy change of combusting 1 mole of the species with essentially excess oxygen. So for glucose, this would be the combustion of solid glucose plus oxygen to produce CO2 gas and liquid water. Now, one of the things you have to watch out for is if I'm actually conducting a combustion, especially under non-standard state conditions, I may not be producing liquid water. I may be producing gaseous water. I may be making steam. And in that case, I'm going to see a very different set of enthalpies. And again, you can see that the enthalpy of formation of glucose is much less than the enthalpy of combustion. Now, one of the great things is that as long as all of my enthalpies are in terms of formation or combustion, I can simply take the enthalpies of every given species in a reaction, plug it into this simple difference, and get an enthalpy of reaction. But again, one of the nice parts about Hess's law and its essentially description of thermodynamic functions is that I can go ahead and combine any type of reactions I have to produce new sorts of reaction enthalpies. And we can actually see this by looking at the enthalpy of combustion of glucose. Say, I want to go ahead, instead of figuring out the enthalpy of combustion of glucose producing liquid water, I want to see what the energy change is if I'm producing steam. So I'm going to need a subset of reactions to make use of. So for example, I'm going to need the combustion of glucose, and then I need to have an additional reaction where I turn water into steam. For that, I can make use of my enthalpy of vaporization, which is again just another reaction enthalpy. And then I can go ahead and combine these two together. Now, if I'm going to be combining these reactions together, I'd have to essentially add in 6 of this reaction. My 6 waters cancel out, and I'll have 6 water molecules in the gas phase. So again, I'm doing the same thing with my enthalpies, where I'm going to take the enthalpy of combustion plus 6 times the enthalpy of vaporization. And what I end up is an enthalpy of negative 250 of 2,537 kilojoules per mole. So this is a much less exothermic reaction, as it's producing much less energy than if I was producing just liquid water. And this is entirely due to the fact that, well, it turns out that there's a lot uh, that I had to spend some of that energy to essentially just break the IMFs in the water molecules themselves. So this is the simple idea behind a lot of our thermochemistry and and how we can combine chemical reactions to describe the enthalpies of a whole different set of species. Now, most of this we've talked about in general chemistry. However, next time we need to try and figure out how are these enthalpies going to be modified if I start working under different conditions. That one's just a little bit important. So next time, we'll talk about temperature dependence. Till then, take care.